All right, let's jump right into this explainer because today we are unraveling one of the absolute most extreme mechanical challenges out on the ocean, marine steam turbines, and the massive gearboxes that tame them. Believe me, if you get this wrong, you don't just lose efficiency, you can literally shake a massive gearbox to pieces. So let's get into it.
Section 1. The Great RPM Mismatch. To really understand a marine steam propulsion plant, we have to start with the core engineering paradox that dictates its entire design. It all boils down to a fundamental disagreement between what the engine naturally wants to do and what the propeller actually needs to do.
Take the number 6,000, for example. A modern marine steam turbine rotor spins at a blistering 6,000 revolutions per minute. Just to put that into perspective, that is 100 times faster than the propeller it's driving actually needs to turn. The turbine is specifically designed to spin at an absolute blur just to be efficient and generate its power.
But then, on the other end of the ship, we have the propeller. Now, for a propeller to efficiently grip the water and thrust a massive ship forward without causing cavitation, which is where those destructive vapor bubbles form and chew up the blades, it needs to turn slowly. We're talking around 85 revolutions per minute. This gigantic speed mismatch is exactly what hides one of the cleverest pieces of mechanical engineering on the entire vessel. I mean, how on earth do you bridge the gap between 6,000 RPM and 85 RPM without tearing the ship apart?
Well, that brings us to Section 2, how steam turbines work. Because before we figure out how to step that speed down, we need to understand exactly why the turbine spins so incredibly fast in the first place.
So here's the deal. A steam turbine relies on expanding steam rather than explosions inside a cylinder. It converts the thermal and pressure energy that's stored up in high-pressure steam directly into rotational kinetic energy. And get this, there are absolutely zero pistons, no reciprocating parts whatsoever. Because you don't have these massive metal components constantly reversing direction, the turbine generates enormous power with an extremely smooth, low-vibration output. Historically, that made them the absolute perfect choice for vessels like LNG carriers. When you're transporting a highly pressurized cryogenic cargo, you obviously want as little vibration as humanly possible.
Section 3. Impulse versus reaction blading. To achieve that incredibly smooth, high-speed rotation, engineers use two highly specific methods to harness the energy of all that expanding steam blasting through the casing.
There are two distinct approaches to this problem: impulse blading and reaction blading. To get your head around it, think of impulse blading literally like aiming a high-pressure fire hose right at a paddle wheel. The steam expands and speeds up in these fixed nozzles before it hits the curved moving blades. So the sheer velocity of the steam jet smacking into the blades is what pushes them forward. On the flip side, reaction blading works exactly like a rotating lawn sprinkler. In this setup, the steam expands and accelerates as it passes through the moving blade passages themselves. So the blades are essentially acting as nozzles, and the steam accelerating out of them pushes the blades backward via a reaction force.
But what's really fascinating is that real marine turbines don't just pick one or the other. They're almost always hybrids. They use impulse stages at the high-pressure end, which is where you need a really large pressure drop per stage, and then they seamlessly transition to reaction stages toward the low-pressure end. It's this brilliant hybrid approach that perfectly balances thermal efficiency against the intense mechanical stress on the blades.
But, as you can imagine, this is where the physics start fighting back. Welcome to Section 4, Taming Extreme Internal Forces. Harnessing all of this high-pressure steam and turning it into rotational energy creates some absolutely terrifying internal pressures inside that casing.
Remember how we said reaction blading acts kind of like a rocket pushing backward? Well, when you have thousands of blades doing that all at once, it generates a massive axial thrust. It literally wants to violently shove the entire rotor straight out the front of the casing. So, to stop that from happening, engineers use something called a dummy piston. They actually pipe high-pressure steam directly to a piston mounted on the rotor, and they carefully size it so that the steam pressure pushes backward with the exact same force that the blades are pushing forward. It is a perfectly balanced, incredibly elegant counterforce.
Then there's the whole sealing problem. I mean, how do you keep high-pressure steam from just blasting out of the spinning rotor shaft ends? You definitely can't use rubber seals at 6,000 RPM. They'd melt in seconds. Instead, the solution is labyrinth glands. These are a literal maze of winding clearance passages between the rotor and the casing. The steam is forced to navigate this super tight, winding maze, and as it does, its pressure drops progressively until it hits zero. When you combine that with a gland steam sealing system, it creates this invisible, frictionless barrier that keeps that extreme high-pressure environment perfectly sealed inside.
Moving on to Section 5, the reduction gearbox. Okay, so we've safely harnessed our steam, but we are still stuck with our original problem. The propeller needs 85 RPM, and our turbine is spinning at 6,000. It's time to step that speed down.
Now, I want you to pause for a second and think about this from a mechanical design standpoint. If you're a naval architect, could you just build a single gear reduction stage to drop 6,000 RPM all the way down to 85 RPM in one clean step? Really think about whether that would actually work.
The answer? Absolutely not. No way. To hit a 70-to-1 reduction ratio in a single step, the final gear wheel would have to be so astronomically large, it literally wouldn't even fit inside the hull of the ship. It would be completely, 100% impractical to manufacture, install, or operate.
So the actual solution is a double reduction helical gearbox. You basically split that massive ratio into two manageable steps. The energy flows from a small, unbelievably fast primary pinion gear right into a larger primary wheel. That primary wheel shares a shaft with a secondary pinion gear, which then meshes with the massive, slow main gear wheel that's actually attached to the propeller shaft. And because the gear teeth are helical, meaning they're cut at an angle, you have multiple teeth in contact at all times. That's the secret to making sure the transfer of that monstrous load is perfectly smooth and quiet.
Now, sometimes things are incredibly tight in the engine room, and even a traditional double reduction gearbox is just too big. In those scenarios, marine engineers turn to epicyclic or planetary gears. This is just a brilliant mechanical arrangement where you have a central sun gear, orbiting planet gears, and a stationary outer ring gear. It manages to achieve those huge speed reductions in an incredibly tiny, compact footprint that sits directly in line with the shaft.
Section 6, surviving the sea. We have to remember, we aren't operating this equipment in some clean, stable laboratory on land. We are running this machinery in the brutal, totally unpredictable environment of the open ocean.
This analogy absolutely nails how these two systems have to interact. Think of the turbine as a cyclist pedaling flat out at a blistering cadence on a super lightweight bike. Now think of the gearbox as the bike's transmission, taking that incredibly fast, light pedaling and converting it into the slow, crushing, powerful turning of a heavily loaded wheel hauling itself up a steep hill. You absolutely need both halves working in perfect harmony. If one fails, you aren't going anywhere.
And when you actually look at the scale of this harmony, it's pretty mind-bending. A classic steam turbine LNG carrier plant might easily pump out over 30,000 kilowatts of power. The gearbox isn't just lazily slowing the turbine down, it is actively surviving constant, massive torque reversals every single time an ocean wave crashes against the propeller, constantly varying the load. To handle that much raw power at a 70-to-1 ratio, the gear teeth on these massive steel wheels have to be cut to tolerances measured in microns. We are talking about microscopic precision on machinery the size of a two-story house. And by the way, this exact same gearing principle, a fast prime mover driving a slow propeller, is exactly what geared medium-speed diesels use too, which we actually covered back in episode 1.1, just with slightly smaller ratios.
And that brings us to an absolutely vital piece of practical watchkeeping advice for anyone down in the engine room. Because these gearboxes are cut to such extreme, micron-level tolerances, any gear tooth wear or slight shaft misalignment is going to show up first as noise. Specifically, you're going to hear a distinct whine at specific harmonic frequencies. You have to treat any new gearbox whine as an early failure warning. It is not just background noise to tune out. It is quite literally the sound of microscopic metal failure that is very quickly going to turn into a macroscopic disaster.
Which really leaves us with this final provocative thought to chew on. You've got this delicate, finely tuned turbine screaming away at 6,000 RPM on one end, and the violent, crushing, totally unpredictable torque of the open ocean on the other. And the only thing standing between them is a set of gears cut to the width of a human hair. When the ocean pushes back and just a single micron cut tooth begins to fail, what do you think happens next? That tension right there is exactly what makes marine engineering such a thrilling discipline. Thanks so much for joining me on this explainer, and keep your curiosity sharp.